Hi everyone. In this video we're going to continue talking about hypothesis testing, and now this time we're going to talk about for a population proportion what that would look like. And so let's get right into it. First, let's explain the logic of hypothesis testing. So let's start with this idea from this example. A politician hires a polling firm to obtain a random sample of 1,000 registered voters in her district and finds that 534 of them are in favor of a certain policy. And so in that case, our sample proportion, or p hat, is 534 out of 1,000, or 0.534. So the question is, did these results suggest that among all registered voters, more than 50% favor the policy? Or is it possible that the true proportion of registered voters who favor the policy is actually 0.5, and that we just happen to survey a majority in favor of the policy? So in other words, we're wondering, would it be unusual to obtain a sample proportion equal to the one we got, 0.534, or higher from a population whose proportion is believed to be 0.5? What is convincing or statistically significant evidence? All right, so when observed results are unlikely under the assumption that the null hypothesis is true. So remember, we've talked about this. The null hypothesis is like the default one. We say that the result is statistically significant and we reject the null hypothesis. So to determine if a sample proportion of 0.534 is statistically significant, we're going to build a probability model. So remember our criteria that we can check for normal distribution. It's these three things. So since the sample data are from a simple random sample, that's the first one to check. Because this calculation, our sample size times p times its complement, is greater than or equal to 10. And then the third thing, the sample size is sufficiently small, less than or equal to 5% of the population. Then with those three things true, we can use a normal model to describe the variability of our parameter, p hat. So the mean of the distribution of p hat, denoted mu sub p hat, is 0.5, and the standard deviation, denoted sigma sub p hat, remember our calculation for that, is actually going to be about 0.016. Okay, so here is our normal curve with some values. This is our sampling distribution of our sample proportion p hat from our example. So notice our mean was here, our supposed proportion, and then plus 1 standard deviation away from the mean and minus 1 standard deviation away from the mean. Okay, so there's actually two approaches that we can use to test if a majority of the politicians' constituents are in favor of the policy. The first one is called the classical approach, and here's the logic of it. We may consider the sample evidence to be statistically significant, or you can just call that sufficient, if the sample proportion is too many standard deviations, like 2 standard deviations, above the assumed population proportion, in this case 0.5. And so from our simple random sample, our sample proportion was 0.534, and so our corresponding z-score, plugging it into our formula, is 2.15. And so that's our number of standard deviations away from our mean. So 2.15 standard deviations above the hypothesized proportion of 0.5. So therefore, using our criterion that we just mentioned about being too many standard deviations away from the mean, which we said was 2, the number 2, we could reject the null hypothesis. Okay, this is more than 2. And so why does it make sense to reject the null hypothesis if the sample proportion is more than 2 standard deviations away from the hypothesized proportion? Well, here's our curve and the area under the curve. So 2 standard deviations away from our mean. If we look at the area to the right of that, it's only 0.0228. That's about 2.2%. And the area to the left of that is 97.72%. So another way to say this is that if the null hypothesis were true, that the population proportion was actually 0.5, then 97.72% of all sample proportions will be less than or equal to 0.532. So where that 0.532 came from, it was our mean plus 2 standard deviations. Okay, so that's 0.532. And then that would also mean that only 2.28% of the sample proportions would be more than that value. Okay, so then for hypothesis testing using our classical approach, if the same sample proportion is too many standard deviations away from the proportion stated in the null hypothesis, then we reject the null hypothesis. So for us, for our example, the sample proportion was too far above. It was 2.15 standard deviations away from the proportion of 0.5. And so we reject the null hypothesis, and we could say that there was sufficient evidence to conclude that the majority of registered voters were actually in favor of the policy of the politician. So the next approach is called the p-value approach. So a second criterion we may use for testing hypotheses is actually to determine how likely it is to obtain a sample proportion when we know our population proportion. So for us, that sample proportion was 0.534, and our population proportion is 0.5. So if a sample proportion of 0.534 or higher is unlikely or unusual, then we can say that we have evidence against the statement in the null hypothesis. Otherwise, we do not have sufficient evidence against the statement in the null hypothesis. So we can compute the probability of obtaining a sample proportion of 0.534 or higher from a population whose proportion is 0.5 using our normal model. So what we're looking for is the probability or the area under the normal curve to the right of 0.534. And so we can compute this probability by hand or using our technology. And so by hand, we could say we're looking for the probability that p hat is greater than 0.534. We can convert that number to a z-score, which we already did earlier, and we're saying this is equivalent to the probability that z is greater than 2.15, and we would get, using our standard normal distribution table, that area to the right is 0.0158. So let's do this real quick also using StatCrunch. Okay, so I'm going to go to Stat Calculators and down to Normal. And we have, we can do this with the z-score. Let me show you that one real quick. We already know that the z-score was 2.15. So we want x, in our case this would be like z, greater than 2.15. And we would get 0.01578 if we round. It would be the area to the right. Let's do this though also with the p hat value. So our mean was 0.5. Our standard deviation, we rounded it to 0.016, but it's going to give a rounding error. So I'm going to, if I type in my calculator, our standard deviation calculation, it's actually 0.015811388. That's just going to be more accurate than my rounded version of 0.016. And we want x greater than or equal to 0.534. And compute, and we get the same area right over there. Same probability. So the value of 0.0158, which that's about 1.58%, which rounds up to 2, is called the p-value, which means about 2 samples out of 100 will give a sample proportion as high or higher than the one we obtained if the population proportion really is 0.5. Because the observed results are unusual, we take this as evidence against the statement in the null hypothesis. So a p-value is the probability of observing a sample statistic as extreme or more extreme than one observed under the assumption that the statement in the null hypothesis is true. So to say this a different way, the p-value is the likelihood or the probability that a sample will result in a statistic such as the one obtained if the statement in the null hypothesis is true. And so for our hypothesis testing, when we use this p-value approach, if the probability of getting a sample statistic as extreme or more extreme than the one obtained in small under the assumption the statement in the null hypothesis is true, then we reject the null hypothesis. All right, so here's what it comes down to with our p-value. The lower the p-value, the stronger the evidence against the statement in the null hypothesis. And so we just have a table here with different values for p. So if our p-value is greater than or equal to 0.10, that's saying greater than 10%. What we say is we don't actually reject the statement in the null hypothesis. The evidence is consistent with the null hypothesis. If our p-value is between 0.05 and 0.10, so between 5 and 10%, that means that there's some evidence against the statement in the null hypothesis. If we keep getting lower, a lower p-value, now between 1% and 5%, we move up and say that there's moderate evidence against our null hypothesis. And then 0.001, which is 0.1% and 1%, there's strong evidence against the statement in our null hypothesis. And then if our p-value is less than 0.1%, we say there's very strong evidence against the statement in our null hypothesis. So the lower the p-value, the stronger the evidence against the statement in the null hypothesis. So the figure illustrates our politician example for both the classical and p-value approaches to our hypothesis testing. The distribution in blue shows the distribution of our sample proportion, this one here, assuming that the null hypothesis is true, that our population proportion is actually 0.5. And then notice our sample proportion of 0.534 under here with the red is too far to the right in this case from the assumed population proportion. So our possible distribution of p hat, assuming our null hypothesis is false. So because this distribution for our sample proportion of 0.534 is too far away from our distribution, if our null hypothesis was true, we would say that we'll know our population proportion is actually greater than 0.5. And so we reject the null hypothesis that p is 0.5, and we conclude that p must be greater than 0.5, indicated by this distribution in red over here. Okay, so now let's actually test some hypotheses about a population proportion. So we're going to be testing our hypotheses regarding our population proportion p, and we're going to break it into some steps. So step 1, determine the null and alternative hypotheses. The hypotheses can be structured in one of 3 ways. So we've talked about this previously. We have a two-tailed test, left-tailed, and right-tailed. And then remember, H0 represents the null hypothesis, and H sub 1 is our alternative hypothesis. And so P0 is the assumed value of our population proportion. Step 2 is to select a level of significance, which we call alpha, depending on the seriousness of making a type 1 error. Okay, and then remember we talked about this also previously, the types of errors. Type 1 error said that we reject the null hypothesis even though it was true. Okay, so that's a type 1 error. And then we would continue on, provided that the sample is obtained by simple random sampling, and our calculation n times our p0 value times its complement is greater than or equal to 10, and that the sampled values are independent, and the way to check that is if our sample size is less than 5% of our population size. So we've been checking these 3 things for a while to see if we can use our normal distribution, so we just continue to check those. So we're going to do this using the classical approach first, and then we'll also do the p-value approach. So step 3 will be compute our test statistic. So converting to our z-score, we're just calling it z0 based on our p0 value. Okay, so this is just our parameter p hat minus our mean p0 over the standard deviation. So we would get our z-score. And then we use our standard normal distribution table that we've been using for quite some time now to determine the critical value. So if we're using the two-tailed test, we're going to get 2 critical values. The left-tailed test, we get our negative z value here, z sub alpha, and the right-tailed is going to give us positive z sub alpha. And then we compare the critical value with our test statistic. So for the two-tailed test, if our z-score z0 is less than our critical value, our negative one, or our z-score is greater than the positive critical value, we reject the null hypothesis. For the left-tailed test, if our z-score is less than our critical value, we reject. And if it's a right-tailed test, if our z-score is greater than our critical value, we reject the null hypothesis. And then step 5 is to state our conclusion. So same process as far as our what we're trying to accomplish here, but now we're using the p-value approach. So we're going to start back over at step 3 and compute our test statistic, finding our z0 value. Then we use our standard normal distribution table to find our probability corresponding to our z value that we calculated. And so for the different p-values, depending on our test, for the two-tailed test, we're going to get a p-value that's 2 times that probability from our table. For a left-tailed test, we look at our table and we find the probability to the left of that z value, and then that's equal to our p-value. And then for the right-tailed test, from our table, remember your standard normal distribution table always tells you the area to the left of the z-score. And so for this one, you would say 1 minus the probability to the left. So just remember from the past how that works. The table is going to give you this probability to the left of the z0 value. And you say 1 minus that number, and that's your p-value for the right-tailed test. And then if you want to use technology instead of your table, you can use a spreadsheet or calculator. And so I have directions for you on the next slide for how to use different technologies. And then step 4 is to determine if your p-value is less than alpha, then you reject your null hypothesis. And then number 5 here is to state the conclusion. So here's a step breakdown for the different technologies that you might decide to use for these calculations. A lot of the time we use StatCrunch, but feel free to pause this if you want to read about the different ones that you might be using. So let's try this example. So Humira is a medication used to treat arthritis, and in clinical trials, 705 subjects diagnosed with rheumatoid arthritis were administered 40 milligrams of the drug every other week. Of the 705 subjects, 66 of them reported nausea as a side effect. It is also known that the proportion of RA subjects in similar studies receiving a placebo who report nausea as a side effect is 0.08. Does the sample evidence represent significant evidence that a higher proportion of subjects receiving Humira experience nausea as a side effect than those taking a placebo? So we're going to use alpha equals 0.05 for our level of significance. And so just a quick reminder, the level of significance is just the probability of making a type 1 error. So first, our step 1, identify the null and alternative hypotheses. So the null hypothesis is that the proportion of subjects taking Humira who experience nausea is equal to that of the placebo experiment, which is 0.08. And then remember, the null hypothesis is always a statement of no difference or no change. And what we want to do is determine if the sample evidence suggests that a higher proportion of subjects taking Humira experience nausea as a side effect. So that's going to be our alternative hypothesis. So our null hypothesis, H0, is that P equals the 0.08. And then our alternative hypothesis, H1, is that P is actually more than that. It's greater than 0.08. And so notice that this is a right-tailed test because our alternative hypothesis, we're saying P is greater than the null hypothesis parameter value. And then our next step, remembering that our level of significance is alpha equals 0.05. The data is from a random experiment, so we're just checking our facts here. Our calculation for n times p0 times its complement is greater than or equal to 10. And knowing that our sample size is less than 5% of the population, so the sampled values are independent of each other. And so we can use our normal distribution. So for the classical approach, or assuming the statement in the null hypothesis is true, so our p0 value would be 0.08, and then our sample proportion would be p hat is the 66 out of 705. So that's 0.094. And what we want to know if it's unusual to obtain a sample proportion of 0.094 or higher when the population proportion is 0.08. And so we calculate our test statistic, Z naught, plugging into our formula, and we're going to get 1.37. Okay, and now we are working with the right-tailed test, and so based on our level of significance, alpha being 0.05, we want Z sub alpha, which is Z sub 0.05, which is our critical value. And the critical value for that, which you can get from your standard normal distribution table, is 1.645. And so this area, this region to the right, we'll call that the critical region. And notice where our Z naught value is at. Our test statistic is actually to the left of this region. And so step 4, because our test statistic, 1.37, is less than our critical value, we don't reject the statement of the null hypothesis. And this is because of what we talked about when we were going over our steps. If we have a right-tailed test, we only reject the null hypothesis if our Z naught value is greater than our critical value. Because it's less than, we don't reject. And so just a note, well, we did not reject the statement in the null hypothesis that the proportion of Humira subjects experiencing nausea is equal to 0.08. The p-value suggests that there is actually some evidence to suggest that Humira users are experiencing an adverse reaction. So remember, just because we do not reject the statement doesn't mean we accept the statement. And so our p-value approach, starting at step 3, same setup so far. We calculate our p-hat value. It's going to be 0.094. And we want to know how likely it is to obtain a sample proportion of this value, 0.094, or higher from a population whose proportion is actually 0.08. So we compute our test statistic, Z naught. We get 1.37 again. And then we're going to go to our standard normal distribution table and get the area to the right of our normal curve corresponding to this Z naught value. So let's go over there real quick to see how you got the 0.0853 number here. So for our Z value of 1.37, we have 1.3 here, 0.07 here, and if we line those up, let's see, we get 0.9147. And now remember, this always gives you the area to the left of that Z value, and so what you want to do is you want to say 1 minus this amount, and that's where our 0.0853 number came from. So if we do this in StatCrunch, we're going to go to Stat, Calculators, Normal, and let's just use our Z-score. So our mean is 0, our standard deviation is 1 for our Z values, and we want X greater than or equal to our 1.37. And there we have it, our 0.0853 number. Okay, so our p-value is the probability that our Z value is greater than Z naught. So Z is greater than 1.37, which was 0.0853. And so using StatCrunch, we got actually the same number. And then our step 4, we have to figure out what to do with this information. The p-value of 0.085 means that if the statement in the null hypothesis, p equals 0.8, is true, we would expect to observe 66 or more subjects who experience nausea in about 85 out of 1,000 repetitions of this study, because this is 85 thousandths. The observed results are moderately unusual. However, because the p-value is greater than the level of significance, because our 0.085, our p-value, is more than our alpha value, 0.05, we do not reject this statement in the null hypothesis. And then our conclusion, there is not sufficient evidence at the 0.05 level of significance to conclude the proportion of subjects taking Humira who experience nausea is greater than 0.08. Okay, let's do another one. This time it's going to be a two-tailed test. Which do you think is easier to raise, a boy or a girl? When asked this question in 1947, 24% of all Americans said raising a girl was easier. In June of 2018, the Gallup organization surveyed 1,500 adult Americans, and 408 of them felt it was easier to raise a girl. Does this result suggest the proportion of adult Americans who believe it is easier to raise a girl has changed since 1947? Okay, and so our null and alternative hypotheses. The null hypothesis would be that the proportion of adult Americans who believe it's easier to raise a girl is still the same. It hasn't changed since 1947. And so remember, that's because the null hypothesis is of no change or no difference. And so our alternative hypothesis would be that our sample evidence suggests something different, a different proportion of adult Americans who believe it's easier to raise a girl. That's why this is a two-tailed test, because our alternative hypothesis just doesn't equal the null hypothesis. And so we're going to use a same level of significance from our last example, 0.05, and then just check that our data is from a simple random sample. Our calculation of n times p naught times its complement is greater than or equal to 10, and that our sample size is less than 5% of the population. Okay, and so from our classical approach, we can compute our p-hat value, the 408 out of the 1,500 people surveyed, and so that's 0.272. And so with this classical approach, we want to know if it's unusual to obtain a sample proportion of 0.272 from a population whose proportion is 0.24. So we calculate our test statistic z naught, and plugging in our values, we're going to get 2.9. And so because this is a two-tailed test, we have two critical values. Going back to what we looked at earlier when we talked about this, when alpha is 0.05, for our two-tailed test, we divide that by 2. So we actually want negative z sub 0.05 divided by 2. So 0.025 would actually be the subscript here. And if you look this up in your standard normal distribution table, you're going to get negative 1.96. And for your other critical value, you're going to get 1.96. And so we have two critical regions, one on the left and one on the right. And notice where our test statistic, z naught, is at. It's actually within one of our critical regions over here to the right. And so because our z naught value is 2.9 and it's greater than the 1.96 critical value, we reject the statement in the null hypothesis, because that's what we talked about for the two-tailed test. If our positive z naught value was greater than our positive critical value, then we reject the null hypothesis. Now with our p-value approach, we're going to start it pretty similarly. Our p-naught value is 0.24. Our p-hat value is 0.272 like before. But now what we want to know is if it's unusual to obtain our sample proportion 0.272 from our population whose proportion is 0.24 by finding the probability of that sample proportion. So our test statistic, z naught, is still 2.90. And then we are working with our two-tailed test. And so the p-value is the area under our standard normal curve to the left of negative z naught and to the right of positive z naught, shown here below. Okay. And so to get your actual p-value here, and we had this earlier on our table that we looked at, it's actually the sum of these two probabilities. And so using symmetry, you can just say 2 times the probability that z is greater than your positive z naught value. And so using your table or technology, you can get the probability that z is greater than 2.9, and that's about 0.0019, and 2 times that is about 0.0038. And so if you go to StatCrunch, you're going to get a p-value very, very close to this, just off slightly by one number here. We're going to get 0.0037. So let me show you real quick how to do this in StatCrunch. So this time we're going to go to Stat and down to Proportion Stats. And we want one sample, and we are going to use with summary. Okay, so our number of successes was the 408 out of our 1,500 observations. And our null hypothesis, p was equal to 0.24. And then our alternative hypothesis was that p did not equal that p-value from the null hypothesis. And then we hit compute, and there we have it. And then notice here's our p-value right over here, 0.0037. And so step 4, our p-value of 0.0038 or 0.0037 means that if the statement in the null hypothesis, which was p equaled 0.24, is true, we would expect the type of result observed, or more extreme results than that, in about 4 out of every 1,000 repetitions, because if we round this is about 4 1,000ths. And so the observed results are unusual because the p-value is less than the level of significance, that is 0.0037 is less than 0.05, we reject the statement in the null hypothesis. And so our conclusion is that there's sufficient evidence at the 0.05 level of confidence to conclude the proportion of adult Americans who believe it's easier to raise a girl has changed since 1947. In fact, we are 95% confident the proportion of adult Americans who believe it's easier to raise a girl is between 0.249 or 24.9% and 29.5%. So for our two-tailed hypothesis testing using confidence intervals, we have the following. When testing our null hypothesis, okay, H0 equal to our P0 value, our parameter value. When testing our null hypothesis versus our alternative hypothesis that doesn't equal that P0 value, if our confidence interval, remember how that looks, it's 1 minus alpha times 100%, contains P0. So if our confidence interval contains our P0 value, do not reject the null hypothesis. However, if the confidence interval does not contain P0, conclude that P doesn't equal P0 at the level of significance that we were working with. In this case, our alpha was 0.05. And so for this example here, testing using a confidence interval, a 2009 study by Princeton Survey Research Associates International found that 34% of teenagers text while driving. Does a recent survey conducted by Consumer Reports, which found that 353 out of 1,200 randomly selected teens had texted while driving, suggests that the proportion of teens who text while driving has changed since 2009, and then use a 95% confidence interval to answer the question. Okay, so the 95% confidence interval for P, based on the Consumer Reports survey, has a lower bound of 0.268 and an upper bound of 0.320. And so we're just concluding these values, but you would calculate all of these based on our given information. Remember, we talked about lower and upper bounds previously. And then because 0.34 is not within these bounds, notice it's actually greater than the upper bound of the confidence interval, there's sufficient evidence to conclude that the proportion of teens who text while driving has changed because this value is not within our confidence interval. All right, so our last objective is to test hypotheses about a population proportion using the binomial probability distribution. Okay, so we're going to start with this example. According to the USDA, 48.9% of males between ages 20 and 39 consume the recommended daily requirements of calcium. After an aggressive Got Milk advertising campaign, the USDA conducts a survey of 35 randomly selected males, same age group, and finds that 21 of them consume the recommended daily allowance of calcium. At a 0.10 confidence level, or level of significance, is there evidence to conclude that the percentage of males aged 20 to 39 who consume the recommended daily allowance of calcium has increased? So first step, the status quo or no change or null hypothesis proportion of 20 to 39-year-olds who consume the recommended daily requirement for calcium is our 0.489 number. And we want to know whether the advertising campaign increases proportion. And so notice what we have. Our null hypothesis is that P equals our 0.489, and then our alternative hypothesis is that P is greater than 0.489. And so from our null hypothesis, we know our p-naught value is 0.489, and our sample size was 35. And so checking our criteria here, our n times p times its complement is 8.78. Remember, we always want this to be more than 10 or more. And so because this is less than 10, the sampling distribution of p hat, it's not approximately normal. We can't use our normal distribution in this case. And so we're going to let the random variable x represent the number of individuals who consume the daily requirement of calcium. We have x is 21 successes in our sample size of 35 trials. So our p hat value is the 21 out of 35, or 0.6. And we want to judge whether the larger proportion is due to an increase in the population proportion, or is it due to a sampling error. So we obtained 21 successes in the survey, and this is a right-tailed test because we were wanting to know if our alternative hypothesis parameter value was greater than the value from our null hypothesis. So the p-value is the probability that x is greater than or equal to 21. So we want 1 minus the probability that x is less than 21. These are equivalent. And so less than 21 is 20 or less. So notice there's no equal bar here. X has to be strictly less than 21, but that means x is 20 or less. Okay, so 1 minus probability x is less than or equal to 20. Okay, so we can do this a number of ways. If you use your TI-84 calculator, you can use your binomial CDF function and just do 1 minus that, inputting your sample size and your p-value and your x value. Okay, so you just input those numbers, and this will calculate your p-value for you, and it's going to be 0.1261. And so the p-value is greater than the level of significance. Remember, alpha was 0.10, and we just found out that our p-value is 0.1261. So in this case, because it's a right-tailed test and our p-value is greater than alpha, we do not reject the null hypothesis. And there's not sufficient evidence at this confidence level of significance to conclude that the proportion of 20 to 39-year-old males who consume the recommended daily allowance of calcium has increased. All right, so we learned a lot here, but hopefully you're able to keep track of what's going on with these hypotheses tests, and just know that we have two approaches, our classical and p-value approaches, and just kind of keep track of the steps for how to work with each one and what you're looking for when you're working with each test. That's it. Thanks for watching.